Great, let's get started. So welcome to our talk. Today we're talking about supply chain and supply chain security. And I'm Maya Kaczorowski. I'm a product manager at Google, and I work in security.
And I'm Andrew Martin. I'm a founder of ControlPlane, which is continuous infrastructure and engineering security practices with a focus on containerized deployments. Between us, we've done a little bit of everything from product security to development, pen testing, database administration, and we want to talk about the code that we run in production, how it gets there, and how we know the code we thought we were shipping is the same code as we are running. So, what is this nebulous supply chain? It's anything that we depend upon. In a military scenario, the origins and transit of all hardware and software has to be attested to, both where it's from and who builds it. This protects us against adversarial or nation-state attacks. And pharmaceutical companies, they need to know the provenance of all their ingredients because people are ingesting these things. And of course, kittens, well, they need their next treats. The supply chain for these kittens isn't just the hand that feeds them, but also the distributors of the frisky bits, the warehouses that they were in before home delivery, the manufacturers, the farmers that stewarded the chickens, the food that those chickens were fed. So supply chains can be long and difficult to track. And when there are no guarantees that the upstream supply chain is competent, tracking where these things came from becomes even more important, especially if we're feeding the emperor's cats. So, how does this relate to software? Well, this is a grossly oversimplified software supply chain, but ultimately, a software supply chain is any code that ends up running in production and the trusted mechanisms that build, package, and distribute that code. Software supply chains can be exploited, so bugs in libraries that are depended upon by an application or deliberate vulnerabilities snuck into popular dependencies either in the source code or by compromising the hosting service or the infrastructure provider, or perhaps through a compromised download, through a man-in-the-middle type attack or typo squatting, which is becoming increasingly popular. For example, a library with a hyphen in its name is cloned and re-uploaded without the hyphen. So there are two parallel versions controlled by different people. The attackers, so people can happily resolve and download that dependency because it has the same source code. Their applications continue to run correctly. Then, once the new malicious version has maybe 100,000 weekly downloads, malicious code is added by the attacker, which, for example, dumps the environment variables and posts them to a remote endpoint. That means if the code is run on a build server, which is deploying directly to production, production deployment keys are exfiltrated. So, when we talk about supply chain security, we are talking about protecting against all of these threats. The Equifax hack was an example of a supply chain attack exploiting a vulnerable struts library and compounded by a perimeter-focused network policy that allowed database access and subsequent exfiltration. Detecting the vulnerable struts library through scanning would easily have prevented this. These were well-known and published CVEs. So, other attacks, a malicious but legitimately signed version of CC Cleaner, a Windows cleanup tool, was delivered to users via their official download servers in 2017. The signing key could have been compromised at multiple points in that deployment pipeline. And a similar attack happened with Clair, a malicious but signed binary was distributed.
So what in your supply chain will change if you use containers? First, let's look at what your development pipeline looks like more traditionally with virtual machines. Historically, you might have a monolithic application running on a VM, and to make a change, your developers would have to SSH into that machine or push code changes without necessarily understanding the impact that it has on the rest of your environment. You had to do a lot of manual adjustments, including for maintenance operations like restarts. You might not even know exactly what's running in your environment, which is kind of terrifying, right? You're changing things on the fly. This isn't only hard to debug, but there's very little formal process. You'll do the same thing again next time. You'll just SSH again into your VM to debug, patch, update, restart, or otherwise adjust your application. It's not a great security story, and your ops team is probably not going to love it either because they really don't know what's going on in your environment anymore. Now, with containers, this changes slightly. Things are a little bit different. You can have a pipeline of things that end up in your environment. You can write code and ensure that it meets your desired requirements for build, test, scan, etc., and then deploy it. Microservices are redeployed as individual container images rather than changing specific lines of code. It's easier to debug, and it's also easier to change. This doesn't solve everything, of course. You still have hard problems to solve, like dependency management, and you'll need good integration testing to get that right. Going back to the supply chain in general, we're going to break it down into 5 main components that we'll cover in this talk: the base image, code, build, application image, and deploy. These are the pieces of a secure software supply chain, or in our case, a container delivery lifecycle, or a software development lifecycle, whatever you want to call it. So your base image, this is your from line that you build your container on top of. You choose a base image on which to build your application, which then runs in your container. It's packaged as part of the container itself. Code, it's your application code. It's what comes out of your software development process. Build, this is how you do the build of your container image from your code and various packages. Application image, it's how your final packaged up container image contain your application. And deploy, so now that you have your image all together, it's time to deploy it. When you're deploying your image, you can use something like an admission controller to determine what should actually be deployed in your environment. For example, if the image hasn't gone through all of the steps that we've laid out so far, you can verify, or you can't verify its provenance, which means where it came from, then you might not want to deploy it at all. So altogether, these make up the components that you would need. In this talk, we'll go through for each of these what best practices are, and then what open source tools you can use to help get those best practices. So let's dive in.
So in order to stay secure, testing needs to be baked in. Security testing as early in the development lifecycle as possible. So let's have a look what we can do at each stage of the pipeline. Controlled base images and any external images should be pulled, retagged, and then copied into the organization's local image registry. They can then be subjected to your organization's internal compliance requirements and be rescanned for CVEs or policy on a regular basis. This insulates us from upstream changes or compromise. And hash-based addressing. In the same way that Git tags reference an immutable hash, and the tags themselves can be changed, and are vulnerable to replay attacks, and attacks on the usage of cryptography, Docker image tags are the same. They are just a mutable pointer to an immutable content addressable hash. And latest is just a tag that is transitory and so a possible risk.
In terms of code, you can scan your code for common misconfigurations or analyze dependencies. So first, static analysis of your code will help you find more common security issues, such as cross-site scripting in a web application, or misconfigurations, like leaving secrets in code. This scans your code without actually executing it. In addition to good old manual reviews, there are more sophisticated things you can do here, such as abstract syntax tree analysis to get a good overview of a program like a compiler would. A couple of things to keep in mind with static analysis: you're going to need to plug that in directly to your CI/CD pipeline, for example, as part of your IDE. I often have users ask why they can't do this type of analysis later on when you have your full image built, but at that point, it's already all bundled up, so you actually have to do it here. Also, scanners tend to be language specific, so you might be restricted in terms of your choice of scanners if you're picking a particularly bespoke language or environment. The second item here, dependency analysis, helps you figure out both immediate dependencies and transitive dependencies, that is, dependencies of dependencies. So say you're pulling in open source packages, you'll want to better understand what you're using and that you're using the latest patched version. Or if your organization has a requirement to use one particular library over another one, you want to check that that's actually what's happening in reality.
We also want hermetic builds. This means no inter-build data leakage. For example, a build server sharing a single Docker server and socket could be giving access to all the other builds, intermediate layers that we use during the development and build of those other images. Of course, again, we're caching build dependencies for speed and fast feedback loops, and ideally, all those build dependencies are cached within an organization's estate. Pinning versions for deterministic builds depends upon the size of your team and organization. Pinning versions removes the risk of silent Semver upgrades that introduce bugs, or of the upstream being compromised. However, most operating system repository maintainers will remove the previous version of an application when upgrading it. This means that when the version of a dependency is updated in the remote registry repository, our builds will just break. Arguably, the manual advancement of Semver is better, but we can also trust Semver and the maintainers to some extent. This is dependent upon your organization's risk posture. And to the future, rootless builds. Docker has been heavily criticized over the years for running a root daemon, which means that a breakout or a code execution in the daemon's context is executing on the host as root. Rootless builds are a way of mitigating this privilege, and it just means that the Docker build operation does not require a root user. This has historically been hampered by the fact that user namespaces version 1 is not widely deployed. Tools such as Umochi, Image, Builder, and Kaneko are moving towards a safer rootless build environment, although this class of build time attacks that they're mitigating against are best practice defensive security rather than protecting from in-the-wild attacks right now.
Now that you've built your image, you're going to want to verify that it meets security best practices. So first you can scan for vulnerabilities. This is about decoupling your image into a base image and many layers and verifying those for vulnerabilities. You end up scanning OS components, binaries, jars, tarballs, everything. What happens if you do find a vulnerability? Well, your remediation options fall into 3 common categories. First is just to patch it. If there's a patch available and if it's a severe vulnerability, this is recommended. That's the best option. It's something you should be doing on a regular basis anyways through your Docker build files. The second option to help improve your vulnerability scan results is to just remove packages that you don't need. So a stock system will come with many packages on it that in most cases you won't need to actually run your application. Having those on your system creates a larger surface of attack unnecessarily. And the third option is just taking that to the extreme, which is just moving to a smaller distribution, something like Alpine, Debian Slim, or distroless images. Going back to the discussion on base images, using a smaller base image helps you limit your surface of attack and reduces the potential vulnerabilities in your environment. Next, you can scan for configurations. This is to help ensure that your dev team is actually following best practices. Here again, you scan for things like secrets in code, but also container-specific configurations like images running with root privileges, or running as privileged, or other privilege escalation concerns. By scanning for these things and warning developers early on, you can make it easy for them to do the right thing. You can also scan for policies, which are user-defined. Things like the images must not have any high-severity vulnerabilities or have no exposed ports or specifics like extended file attributes. It's kind of an aggregate of the other types of scanning we talked about. These kinds of policy checks will either happen here as part of your image scans or in the next step as part of deployment.
We have followed all of these best practices and now have a container image that we're ready to deploy to production. Because we have the guaranteed immutability of the image's hash, we can capture the metadata generated in the pipeline and associate it with that version of the image. And we can gate admission to production based upon policy, compliance, and any other metadata that we have gathered from the previous build stages. This can validate that all previous build steps have not only passed, but have not been circumvented, and that a malicious user with write access to the Kubernetes API is unable to deploy arbitrary attack code. The simplest thing to do here is to ensure that every image that is deployed comes from a registry that is defined in metadata inside the cluster, and block any image name that does not match our policy. And finally, runtime configuration. It's all very well to configure these images correctly, but a major difference between a virtual machine and a container is that it is so easy to undo all of the security on a container. Simply adding the privilege flag runs the image unconfined without seccomp, without AppArmor, and also mounts the host devices into the container. It's probably one of the most dangerous flags in the history of computing. So running static analysis on YAML, pod specifications and pod security policies inside the cluster prevents some of these possible configuration footguns. kubesec.io quantifies risk based on runtime configuration of the images that comprise a pod, and can be used during development and as an admission controller to apply more granular levels of policy than pod security policies.
So altogether, as we've seen, running a containerized microservices leads to a fundamentally different security model than for VMs. So to recap what's actually different. First, containers are meant to be short-lived and frequently redeployed. Rather than pushing a single line of code change, you're rebuilding and redeploying the entire image each time. If you have other processes that can take place passively, like patching your OS, for example, you can be constantly doing these. You don't have to have a Sunday 2 a.m. maintenance window. Constantly patching. Containers are also meant to be immutable, so they don't change once they've been deployed. You have content addressability, which means that you actually know what's in the environment. This means that even when you scan your image, when it's still in your repository and it's fine, and then after you've deployed it, you discover a vulnerability, you don't have to scan your live environment. You can just look at your registry to figure out if you're affected. Note that we're talking about image scanning here and not vulnerability scanning. You should still be scanning your live app to check that it doesn't have common vulns. Since you're not changing single lines of code but whole containers, you have a single choke point for everything that gets deployed into your infrastructure. That single choke point is critical and what makes containers fundamentally different, and I'd argue a better security model than VMs. It's how you enforce this governance. It's needed for DevSecOps or DevSecOps or continuous security, whatever you like to call it. So to summarize what the good practices look like before we get into tools here across the whole supply chain or container delivery lifecycle. You control your base images and choose minimal images that let you limit your surface of attack. You write your code, scan it for potential security issues and dependencies. Ideally, you can perform more formal security reviews if you have time. You build the image yourself, and ideally this is a hermetic, reproducible build. You scan the image for vulnerabilities, misconfigurations, and also verify that they meet your policies. And then you enforce specific requirements such that your images, in fact, did come out of your pipeline. When something changes, you can just go back to whatever step that was, when a new vuln is discovered, and you rebuild and redeploy the whole image to fix the issue. Now, this is a lot to get done, and you're probably looking at this and going, oh my God, I only do 10% of what's on the slide right now. I don't think anyone is doing all of these things, but it should at least help you focus your efforts and figure out how to best mitigate the risks in your pipeline. And since there is so much to take on, in practice, what should we do to implement these, and what tools should we use?
Let's have a look at what's available to us today and what's coming tomorrow. Now, this should be caveated. Much of this tooling is still under active development, but we'll go through and have a look at them all in some detail. So, of course, a registry is required to hold base and application images. Docker Hub is the biggest of these. However, it no longer runs vulnerability scanning, but other private registries do. Now, there's always some discussion over Alpine versus Debian base images. However, whatever you use, make it consistent, as base images share storage at rest and copy on write memory at runtime. Ensure that you have proper access control and key rotation for auth to your registry.
Next up, code updates. There are two main projects in the code update space, and they're tightly related. Both TUF and Notary are CNCF projects. TUF, which stands for the Update Framework, is a secure distribution mechanism for signing software package updates. For example, when you update an app on your phone, your OS will tell you, hey, we have an update, time to download a new version, please update. Before it performs the update, though, it verifies that that update came from a valid source. And that works in a closed OS, in a closed system like your phone OS, where everything goes through a central store. However, for your application code, you're pulling from many different GitHub repos, and you can't necessarily do that same kind of check. So that's what TUF is trying to address. Notary is just a specific implementation of TUF for container images. Since more and more applications are being containerized, organizations will more frequently receive containers to run rather than arbitrary binaries to run. Notary helps verify that updates to these container images are legitimate before you apply them in your infrastructure. And this isn't the only reference implementation. For example, there's also an implementation of TUF for over-the-air automobile updates called Uptane. So let's look at TUF a little bit more. TUF helps developers maintain the security of a software system update, even against attackers that compromise the repository or signing keys. It's just a framework, so it's a spec plus a few reference implementations. Now, what kinds of potential threats and attacks do we actually see to software updates? While an attacker might try to install arbitrary software in your system by tricking you into downloading the wrong file. That's what people are the most worried about, I think. But they can also create a malicious mirror to prevent a real update or force you to download an older, unpatched version of the software. A software update can then be considered more secure if, according to the tough spec, it knows about the latest available updates in a timely manner. Any files that it downloads are the correct files, and moreover, no harm results from checking or downloading files. So Tough works by providing package signing and creates a signed metadata file using a key. Fine, that's nothing particularly innovative in the security space, plus a secure key distribution mechanism. The main concept to understand about Tough is that it uses a key hierarchy. So it has a root key, which is trusted, and then you then derive from that root key other keys and delegate trust to those. If you know how certificate authorities work for the public web, it's kind of like that. You have a root CA of the internet that signs intermediate CAs, and those CAs then sign certs for individual websites. Instead of digging more into Tough, let's instead look at the specifics for Notary, since it's easier to understand for containers specifically.
Notary is an implementation of Tough for containers that signs and validates images. When clients upload new metadata files, the Notary server checks them against any previous versions for conflicts and verifies the signatures, checksums, and validity of the uploaded metadata. Notary implements various recommendations from the Tough framework, including survivable key compromise and signing delegation, which essentially just means key delegation. So, best practices. Store the most crucial key, which is the GPG master key, offline. This makes it very difficult for adversaries to compromise the trust chain, and trust delegation allows for very prompt key rotation. One could, for example, rotate CI keys every month or every week. On to pipeline metadata. There is a lot of metadata about artifacts and deployments generated in a pipeline. We generally discard this, but if we keep this information, we can use it to make decisions and report on policy, as well as the efficiency and efficacy of the pipeline. Should we allow builds that depend upon vulnerable components, untested code, that come from untested sources, trusted sources, or are of unknown provenance?
So one project in this space is Grafeas, which is an open source project to audit and govern the software supply chain. And you can use it to track information like versioning and vulnerabilities as part of your container registry. It's just a structured metadata API. It's a key value store plus the verification of the data in that store. Grafeas stores metadata about artifacts, like images, and information about those artifacts, like vulnerabilities. You don't need to only use one source of metadata either. You can have multiple providers. So vulnerability scanners, for example, can each write their own results. Some metadata providers include JFrog, Red Hat CoreOS, IBM, BlackDuck, Twistlock, and Aqua. As your software supply chain grows or evolves, you can just add additional providers. So then the real benefit of Grafeas is that all of your metadata sits in one place. You can query across all of this metadata in real time. This lets you answer interesting information about your images, like if they're currently affected by any recently discovered vulnerabilities. I don't know if you see, I always come back to the same point, like, am I affected? That's always the question that people have. So the Grafeas API has a few key concepts. Let's just go through these quickly. A note is the definition of something that can be found or detected through analysis. It's like a note that you'd scribble in the margin of a book. Think of them as the dictionary of things that Grafeas knows about. There are schemas for various predefined types of notes, and these include package, so which packages are installed, vulnerabilities, where are there known vulnerabilities, discovery, what type of analysis has happened, for example, a scan, builds, what source was this built from, and who built it and which builder was used, image basis, which base image was used, deployment history, when was it deployed, by whom and where, and attestation, which is have policy requirements been met. Altogether, these gives you a pretty good idea of the security properties of your image. An occurrence is the instance of a node. It's when you write new data to a node. It might be the building of an artifact, the discovery of a vulnerability, or the running of a scan. A provider is a source of metadata. It's something like a scanning tool, or maybe a team at your organization that wrote the node. A project is the namespace for metadata. Nodes belong to provider projects, so they belong to the scanner, whereas occurrences belong to user projects. Think of this kind of like an index in a book. So the user project is the index, and the provider project is the book, or books. Each book contains a lot of details about a particular topic and might get updated over time as new editions are published. The index job is to say, oh, there's some more information on that, let me update that reference for you and record that information. Note that I only briefly mentioned attestations. They aren't really parallel to notes or occurrences, but are actually part of these items. An attestation is a cryptographic signature that allows for verification of these pieces. The goal of signing the data is that you can then verify it to ensure that it hasn't been tampered with. This is just a GPG signed piece of information stored as metadata in Grafeas, and at verification time, you use a public key to verify that the signature is the correct one.
In-toto is a framework to provide whole software supply chain security. It provides tooling and metadata and a metadata format to ensure that all steps are performed by the right party, follow the expected policy, use the right artifacts, and report the artifacts that were produced. Its core configuration primitive is a layout. Layouts define what can be done, by whom, what to use, what to produce, and what policy to follow. In-toto layouts are cryptographically signed by a manager to prevent tampering or circumvention. In addition to that manager, or project owner, there are additional in-toto parties. A functionary to enact a step or build stage and produce cryptographic evidence, and a verifier to ensure the functionary's output matches the specification in the layout. Finally, links are used to record information about the execution environment, and these links are cryptographically signed by the party who performed the action. The verification step checks for compliance using link and layout metadata, and this verification can be done in many steps. As you see, continuously, upon installation, when a package is installed, or before deployment in the Kubernetes admission control flow. And to compare these projects, Grafeas has a strict API schema, which means you can't store free-form metadata, but it covers many types of note, including the attestation note, which can be used to attest to arbitrary events or notes. On the other hand, in-toto is more adaptable and supports unstructured or free-form data. It can use various storage backends or metadata transports, and importantly, can chain together attestations to assert the sequence of a whole supply chain. Work has been done to integrate these two projects together, and they may end up converging around some elements of their specifications.
So now let's look at vulnerability scanning. So image vulnerability scanning is meant to detect potential issues with your container image. What's actually possible to detect depends on how deep you go in that scanning, to what depth the tool you use gets to. More in-depth tools will scan OS distribution packages, application library packages. Note that for these, sometimes there's a paid feed from the application. So if your scanner hasn't purchased it, you might not be covered. Compressed formats like jars, wars, and tars. Potentially malicious code like malware, rootkits, and backdoors. And misconfigurations like secrets in code, exposed ports, and file system properties. Recall that your container image is actually made up of layers, right? So when you build your image, you're essentially just generating files by running successive commands. Union mount is a way of combining a bunch of file directories into a single directory that shows all of the content. So for containers, you would actually see all the files each layer together rather than layer by layer. There are two main approaches to image scanning. You either scan each layer individually, layer by layer, or you look only at the top layer of the UnitFS file system, which takes all the files together using the latest version. In both cases, though, vuln scanning generally works by comparing the hash of a particular package to a known package and seeing if it has any known vulnerabilities. Most of the vulnerability information comes from the same CVSS database, but a particular vendor might override some of the scoring based on additional information that they have. The best scanners will analyze multiple sources and will work heavily on refining false positives. This is a really critical step. Like if I was going to start somewhere from today's talk, I would probably start here, because most of the attacks that occur in the wild are just drive-by attacks, right? There are people who are looking for deployments with known vulnerabilities. And I'm not talking about zero-day attacks. I'm talking about things that have been around for years left unpatched. So patching, no matter how unsexy the idea is what really helps protect you against some of these potential attacks. So if you're going to do this, what are some of the options you have? There are 3 widely used open source vuln scanners. CoreOS Clair, Aqua Microscanner, and Encore open source engine. As you'll notice, none of these are standalone projects, but owned by companies with other offerings in the space, like a paid scanner. First off, Clair lets you create an index of container images and the features in them, and then query a central vulnerability database for any information about those features. It's the same hash and compare I was describing before. Images are only scanned at ingest time, which means that when new vulnerabilities are updated in the database, you don't have to rescan the image. You can compare it to existing image scans. Project Harbor, that was announced as a CNCF project yesterday, uses Clair for vulnerability scanning. Microscanner works a little bit differently. It runs as part of a container image build as an executable in your Docker file. If your image has any known high severity issue, Microscanner can actually fail the image build, which makes it easy to include as a step in your CI/CD pipeline. Lastly, Encore open source engine is closer in design to Clair. It's a platform that includes a database of vulnerability information for your images. It runs as a separate container in your infrastructure and creates a searchable list of all the packages, files, and software artifacts, such as Ruby gems and Node.js modules in your environment.
And finally, admission control. An admission controller in Kubernetes is a piece of code that intercepts requests to the Kubernetes API server after the request is authenticated and authorized. There are two types of admission controller in Kubernetes, mutating and validating, or both. And mutating controllers modify object content, whereas validating controllers verify their output. So you might run multiple admission controllers together. If any controller rejects the request, an error is returned to the end user. And there are a whole bunch of these admission controllers, not necessarily related to security. In general, admission controllers decide whether you shall or shall not pass. Kritis is a Kubernetes admission controller that can block builds based on policy. It has a policy engine to test assertions before deploying containers into Kubernetes, and this ensures build vulnerability scanning before deployment, or can continuously verify deployed images as vulnerabilities are updated, and verify build provenance before deployment. Cluster administrators manually attest this image is okay to use or it has been verified, and Kritis will then only allow pods that have been verified to access the cluster. At present, Kritis is not usable outside of GCP, but work is underway to make this application more generic. Here is an image security policy example. We see whitelist images that are latest or a certain digest. We will block admission here if the max vulnerability severity is too high in the attestation we have in Kritis, and we can ignore certain whitelisted CVEs that may not be applicable to our runtime environment. Portieris is another admission controller, this time for Notary, and this enforces content trust, again, at deployment time into the cluster. We can apply different levels of trust for different images, and the mutating admission webhook ensures that Kubernetes pulls the signed version of the image. This enforces trust pinning and blocks the creation of resources that are using untrusted images. Right now, this supports the IBM Cloud Container Registry, Key.io, and Docker Hub, although again, work is being done to make this more generic, and other integrations are on the horizon.
So to bring it all together and to get those photos you missed earlier, an ideal software supply chain has security across 5 elements that we described today: base image, code, build, application image, and deploy. Minimal base images to let you limit the surface of attack, scan your code for potential security issues, complete formal security reviews, and understand your dependencies. Build your image in a hermetic, reproducible way. Once it's built, scan your application images for vulnerabilities and misconfigurations. And at deployment time, enforce any specific requirements you have using the choke point provided by containers. When something changes, like a new vulnerability is discovered in a package that you're using, you can go back to earlier in the supply chain, rebuild, and redeploy the image to fix the issue.
So, the state of the ecosystem. Docker Hub provides official base images that we can trust. Tough protects automatic software deployments from attack and makes them more resilient to compromise. Notary uses Tough to secure Docker image distribution from registries, guaranteeing correctness and freshness. Grafeas holds information about your system's compliance and risk state. In-toto secures build steps with cryptographic metadata, enhancing accountability of the individuals involved in the chain and the ordering of their actions. Clair, Microscanner, Anchor, and Friends are essential to prevent known CVEs being pushed to production, and you can protect your clusters at deployment time with admission control. Kritis, in-toto, Portieris, and KubeSec, and live a happy, fulfilled life, ahead of your vulnerabilities and secure forever. Thank you very much.